All right, let's get right into it. Today, we're going to talk about building a truly production-ready database layer in Go. And look, this isn't some academic exercise. We're talking about real lessons learned from painful production incidents. We're going to cover what breaks, what tools you should actually be using, and how to build a system that's rock solid from day one.
So it all starts with a question that, honestly, it probably feels a little too familiar if you've ever been on call. Picture this. You've got a planned maintenance window. A simple, quick database restart. It should be down for what? 5 seconds? Tops. And yet, somehow, that tiny 5-second blip spirals into a full-blown 10-minute service outage. Suddenly, your service is just throwing errors everywhere, pagers are screaming, and what was supposed to be a total non-event is now a major incident. So how on earth does that happen? Well, that's exactly what we're going to break down.
Okay, so to understand how things went so wrong, we really need to dig into the anatomy of what's called a thundering herd. This thing is a classic failure mode, and it can catch even really well-architected systems completely off guard. So here's what happens. The database comes back online after those 5 seconds, right? Your service, which is running on a bunch of different pods, sees this all at the same time. And what does every single pod do? It tries to reestablish its connection pool. So let's say you have 4 pods, and each one has a max of 25 connections. Well, you do the math. That's 100 connection attempts all hitting your database at the exact same moment. And this is where the cascade really kicks in. At time 0, boom, connections are killed. 5 seconds later, the reconnect storm hits. Then, just 10 seconds in, the database CPU is totally pegged at 100%, and you get what's called a query convoy. It's basically a massive traffic jam for your database. New requests get stuck behind this huge line of old ones, and things just pile up way faster than they can be served. The result? It takes a full 10 minutes for the system to claw its way out of this mess and finally recover. Now, this is the really wild part. Your code? That's fine. Each individual piece of your system is behaving exactly as it was designed to. The catastrophe happens because of the synchronized interaction of all these perfectly correct parts all at once. It's not a code problem. It's a systems dynamics problem. Okay, so we know what breaks. Now, how do we fix it? Well, the first and probably most important solution starts with properly configuring your database connection pool. Let's get into exactly how to tune this thing to make your system way more resilient. So there are 3 critical fixes that'll stop this from happening. First, we're going to add Jitter to connection lifetimes. Second, we need to use a separate, dedicated connection for health checks. And third, we have to implement exponential backoff with Jitter when we reconnect. Okay, let's look at that first fix in practice, because it's so simple but so powerful. It's basically this one line of code. By adding a random duration to the connection's max lifetime, you do something brilliant. Instead of every single connection expiring at, say, exactly 5 minutes, now they expire at 5 minutes plus some random offset. This simple trick desynchronizes everything and stops that self-inflicted thundering herd in its tracks. All right, we know how to configure our pool. The next big question is, which tools should we even use to manage it? Let's talk about choosing a Go driver, because trust me, this decision has a huge impact on both your performance and your safety. And I'm not kidding when I say the stakes are high. Get this, benchmarks show there can be up to a 40 times performance difference between drivers. Yeah, 40. So this is absolutely not a minor decision you can just gloss over.
This table pretty much breaks it all down. You've got database/SQL. That's the standard library one. Its big selling point is portability. You know, it works with different databases. Then there's pgx, which is a pure Go, super high performance driver made just for Postgres. But the one I really want to focus on is sqlc plus pgx, because that combo gives you compile time type safety. And yeah, as you can see, that's what we're recommending as the default for any new service.
I love this mental model for it. Think of database/SQL as the Honda Civic. It's reliable, it works everywhere, it's totally fine. Then you have pgx, that's your sports car. It's way faster, has more features, but it's only for Postgres. And SQL is the autopilot. It literally reads your SQL and writes type-safe Go code for you, perfectly, wiping out entire categories of bugs before they can even happen. So yeah, let's just make it official. The clear, actionable takeaway here is this. If you're building a new Go service on top of Postgres, your default choice should absolutely be sqlc with a pgx backend. You get safety, performance, and schema validation, all at compilation time. It's a no-brainer. Okay, we know how to fix our connection pool, and we've picked out our driver. So now let's put all the pieces together and look at the complete blueprint for a production-ready system. A really robust database layer is built on 4 pillars. First, you need versioned schema migrations for safe, reversible changes. Second, that jittered connection pool we just talked about. Third, the repository pattern, which is great for separating your business logic from your database code. And fourth, this really cool technique called the transactional outbox pattern for reliable background jobs. I absolutely love this quote because it just hits the nail on the head. Every single number in your pool configuration, the max connections, the idle time, the lifetime jitter, it's not just a random number you pull out of thin air. It's a lesson. It's a lesson learned from a real painful production failure. Your configuration is the documentation of your incidents. So let's zoom in on that fourth component, the transactional outbox. This pattern lets you use a simple database table as a super reliable job queue. And this is awesome because it means you can handle all your async work without having to bring in the complexity of an external message broker like Kafka or SQS. And don't think for a second this is some lightweight solution. We're talking about handling around 10,000 jobs per second on a single Postgres instance. That is easily competitive with a lot of dedicated cloud queuing services out there. So what's the secret sauce here? Well, the magic is this one SQL clause. Select for update, skip locked. This lets a bunch of your workers safely grab jobs from the queue table all at the same time. The for update part locks the rows so nobody else can touch them. And the skip locked part tells all the other workers, hey, if it's locked, just ignore it and move on to the next free one. You get no double processing, no race conditions. It's just elegant and incredibly effective. Okay, we've covered a ton of ground. So to wrap things up, let's boil all of this down into a concrete, actionable checklist, something you can use to go audit your own systems right now. All right, here are the 4 most critical things you need to do. Number 1, add jitter to your connection lifetimes. Number 2, isolate your health checks, your Kubernetes liveness probes, onto their own dedicated connection. Number 3, ensure type safety by using sqlc. And number 4, make sure your service reconnects smartly after a failure, using exponential backoff with, you guessed it, jitter. And let's end on this really crucial point. None of this is about architecture for architecture's sake. We're not building something complicated just because it looks cool. Every single piece of this design, from the jitter to the driver choice to that outbox pattern, it's a direct response to a real-world production failure. This stuff is battle-tested. So I'll leave you with this question to think about for your own services. Go take a hard look at your database configuration. Is it a document that reflects the lessons you've learned from past incidents? Or is it just sitting there, waiting to cause the next one?